All right, welcome MEGen 301. Tonight we're talking about failure modes and effects analysis. So in this class so far, we've been working on designing a system. We've been designing these plastic shredders where we're trying to put material into the shredder, chop it up into little pieces that we can then recycle the plastic for further uses. And so far we've been focusing on things like, what does this system look like? How do we know how to size the motor for this system so we have enough speed and torque to cut through the plastic? And then how robust is the system going to be? So we did a bunch of FEA analysis to figure out and make sure that all the components in our shredder aren't going to break when we load them up. Today, what we're talking about, this is a concept of how reliable is this system going to be. So we're going to do an analysis to figure out how our system could fail, and then predict those ways that we could fail, figure out how likely it is that those failures could occur is ultimately where we're going, and then you can use that information to design your system so that it will be more reliable or ensure how reliable it's going to be. So to lead off here, I'd like you to take a look at this video from the United States Chemical Safety Board. So the Chemical Safety Board is a government agency that comes in and investigates big industrial disasters that happen in places like oil refineries and other sort of places where chemical engineering, chemical processes happen. So this particular problem that happened was at an ExxonMobil refinery in 2015 where there was a large explosion. So take a minute. I'm going to put a link to the CSB's video down in the description below on YouTube. So go ahead and pause the video here and go watch that if you haven't seen it already. And then we will continue on talking about this failure and kind of how it pertains to what we're doing here in this unit of the class. So I like this video a lot because a lot of times when we're studying engineering failures, what kind of comes across is that the company that was in charge of this facility that failed was just a bunch of idiots and didn't do anything right, and they had a massive explosion, and you think, well, if I had been there, that definitely wouldn't have happened. In this case, you can kind of see that they did most things right, actually. They did a lot of stuff right, but there were a few oversights that led to a big problem, and that could have been really, really bad. Fortunately, there were no deaths in this accident. There were only minor injuries, but there were some pretty serious near misses, right? So there was significant damage to their refinery, and shrapnel did hit a hydrofluoric acid tank, which is an extremely nasty chemical and could have been a huge deal if it had ruptured and leaked that chemical out. But fortunately, that did not happen. Okay, so we just want to talk about what happened here and what does this teach us about why we do FMEA. All right, so the Chemical Safety Board's report gave 4 areas of emphasis that they go into, and they talk about what we can learn from this failure. And I think that they kind of answer a few questions, like what the CSB focused on here is we can ask a question that's really common to a lot of engineering systems. So I'm just going to highlight these 4 questions, and then we'll kind of talk about how we answer those with this sort of analysis that we're doing. So the first thing the CSB highlights is that there was a lack of safe operating limits and operating procedure. And really what that point is addressing it brings up the question of how do we as engineers instruct our users to use our designs safely and effectively. So we have a tool to answer this question, which you'll be doing later on in this class, called this SOP, or the Standard or Safe Operating Procedure. And that's a detailed step-by-step instruction set on how to start up, operate, and shut down some sort of complex engineering system. The idea is you can hand that SOP to somebody, a plant operator, and as long as they follow your instructions exactly as you've written them down, they're not going to get themselves into trouble with your engineering system. So it takes a lot of thought to carefully lay out how to write one of those and make sure that you guide someone who's trying to operate your design step by step in a way that they're going to be able to use your machine safely. Okay, so that'll be coming later on in this class. The next 3 questions are what we're going to be talking about during this sprint here. All right, the second takeaway that the CSB had was the safeguard effectiveness of ExxonMobil's safeguards in their system, right? So in the video, when you watch it, they had the electrostatic precipitator, the ESP, was energized while they were doing repair work on the system. So they have this big electrical system with a lot of sparks in it near a bunch of hydrocarbons, and that spark system is turned on while they're doing work. So this kind of question that we're asking here is, how do we design our systems so that they fail safely? Can we think through of how our system is designed so that if a failure occurs, that we don't get a big catastrophic result? So had the ESP been shut down while they're doing maintenance work, there wouldn't have been nearly as many ignition sources for hydrocarbons to find, and you probably would not have had that big explosion. Okay. Next question, or the point that CSP brings up here, is operating equipment beyond its safe operating life, right? So the slide valve that was supposed to hold the catalyst in place in this cracker unit was eroded, so it had holes in it, and that meant the catalyst was just able to pour through the slide valve even when it was closed. So the question that this sort of points to is, how long will our designs last? How we figure out how long the design is going to last, and then how do we know when we need to do maintenance on a design? Can we plan for that at the design stage rather than having to wait for our design to fail and then go back and fix it? Okay, and then the last one here is they reused a previous procedure variance without sufficient hazard analysis. So you notice in the video they talk about how they just pull some old variance off the shelf and they assume that it would be fine without looking at the current situation that they were facing, which was similar to what they did before, but not exactly the same, and it resulted in a bad outcome. So the question that this sort of points to is, how can we anticipate failures before we happen? And that's really what the main point of FMEA is we're trying to anticipate these failures and plan for them before we let the failures actually happen. All right. So the tool that we're going to use to answer these three questions here is going to be a risk and reliability engineering analysis. So risk and reliability engineering is an entire field of engineering that you can go into and make a career in if you'd like to. It's all about predicting and mitigating failures of engineering systems. So looking at complex engineering systems, figuring out how they're going to fail, what the likely failure modes are, and then figuring out ways to mitigate those and make sure that those engineering systems are as safe as possible. There's a ton of analysis tools used in various industries that are part of risk and reliability engineering, or kind of under that field. We're going to use a specific one of those tools called failure modes and effects analysis, or FMEA. All right. So what we're talking about here with FMEA is, we're just break the acronym down here. The first part is failure modes. So that is, what are the different ways that an engineering system can stop functioning normally, right? So a failure doesn't necessarily have to be a big catastrophic explosion. It can be, for sure. But in engineering, a failure is just considered some sort of deviation from the normal operation of the system. Okay? So that's what we're talking about with failure modes, all the different ways that a failure can happen. And then the effects, we're talking about what are the consequences of one of these failures occurring. So FMEA was developed in the 40s and 50s by the U.S. military because they were trying to increase the reliability of military hardware. Obviously, we don't want to have your military hardware failing when you're in the middle of combat. That could have really disastrous consequences. So they have a vested interest in making sure that military hardware is extremely reliable. Okay, a ton of techniques have been derived from FMEA for different industries. So if you go work in oil and gas or some sort of other place where chemical engineering gets done, a lot of times you'll hear about a hazard and operability study, or HAZOP study. And that's a technique that's very similar to FMEA. It was actually derived from FMEA, but kind of customized to that field a little bit. Also in manufacturing engineering, you'll hear design review based on failure mode, DRBFM. So again, same idea as FMEA. It's derived from FMEA, but then just customized to manufacturing. Okay, so the idea here is we want to give you an exposure to FMEA because it's kind of the granddaddy of all these techniques anyways. So if you go out in your career and you're starting to do a risk and reliability engineering analysis on some system that you're working on, you might be using a different tool than FMEA, but it should look fairly similar because chances are that tool has been derived from FMEA. The tools on the line items that we have on the previous slide are all different techniques for doing this sort of risk and reliability engineering analysis. Again, we're going to focus on FMEA because it's sort of the original technique that all of those techniques are generally derived from. It's still very common in industry to use FMEA. It's probably the most common sort of risk and reliability engineering analysis that's still done. And in this class, we'll be following the original FMEA procedure, which is outlined in this document called MilSpec 629A. A very catchy title there. It is a 1980 revision of the original 1949 FMEA method, okay? And it specifies a two-step approach to doing a risk and reliability analysis. So the first one is just called, they call FMEA, right? And that's where we identify all the failures and their consequences. And then the second step, which we'll talk about in a separate video, is called FMECA. So failure modes, effects, and criticality analysis. So that is looking at how likely different failures are to occur. So first we identify all the failures, and then we go back and we determine how likely each of those failure modes is to occur. And based off of the likelihood of those failures happening, we'll prioritize the failures that are more likely as being a higher level of priority for us to address. Okay, so that's kind of the flow of what we'll be doing. Today we're just going to talk about FMEA, and then in our separate video we'll give you one on FMECA because there's a little bit more math behind that. All right, so the FMEA process has a very sort of defined flow that you work through, okay? The first step that we got to do is we got to define our system. After that, we'll look at how all the parts in the system relate to one another. So we'll construct a block diagram, or how we've been calling a glass box diagram in this class. We essentially want to break down the system and figure out how all the parts relate to one another. Then we'll go through that flow diagram, the glass box diagram, and find components and brainstorm how those could fail. And we'll think of as many ways that each of those components could stop doing their function, right? Then we'll look at each failure mode in terms of what's the worst potential consequences that could result from that failure actually happening. Then we'll talk about how we could identify that failure happening. So, if this part fails, how do we know that it's failed? And then we'll talk about what's some sort of corrective design or other actions could we take to either eliminate that potential for failure or control the risk of that failure. Okay, so we'll talk in more detail here for the rest of this video about what that process looks like, but that's the broad overview of how this process works. All right, so first step is defining a system. This is very important, especially if you're working on a complex system where you might have separate teams working on different subsystems of the overall system, right? So you want to clearly define the scope of your analysis and sort of the boundaries of your system, so you're not analyzing from this part to this part and everything that happens in between, and then maybe there's another team taking off on either side of what you're analyzing. Okay. Part of this, we also want to know what is the function of the system, right? So what does the system need to be doing to be considered operating normally, right? And remember, we want to define what a failure is, and to define what a failure is, we need to know what's normal operation. So think about the function of your design. What is it supposed to do? And then if it stops doing that, you can consider that a failure. All right, now this next step is pretty important also, is you want to just define for the team what constitutes a failure of the system, okay? So remember, a failure can just be any sort of deviation from that normal functioning of your system. And you can change your definition a little bit based off of the needs of your analysis, right? So generally, FMEA is focused on safety. So like a failure is something that could result in injury, right? Would be a severe failure, right? But it doesn't necessarily have to be focused on safety also. You could also talk about, like, if your product quality falls below a certain threshold, that's considered a failure of the system. Or if you have downtime, like your system can't run for a while because it has to be maintained, that can be considered a failure of the system also. So you can tailor this technique to meet the needs of different types of systems that you'd have to analyze. All right. So once you've got your definition of what your system is, what the function of your system is, and what constitutes a failure of your system, then you can go ahead and you can start doing a block diagram or glass box diagram of your system. All right, so you want a detailed diagram that shows all the parts in your system, what the function of those parts are, and how they relate to one another. Okay, it's very important to be able to visualize how the system functions, because remember, we're going to be talking about if one part fails, what happens as a consequence of that. So we need to know how each part in the system relates to all the other parts. Okay, it's important to have a high level of detail here so that you can determine what could possibly go wrong with the system. Okay, from once you have a nice flow diagram that you are convinced is thorough and really documents how all the parts in the system relate to one another, then it's time to go through and identify your potential failure modes. So you go through the glass box diagram point by point, looking at each component, and you want to identify the function of the component. So what is it supposed to do during normal operation? Then as a team, you brainstorm all the possible ways that that component can stop functioning, right? So for some components, there might be, very straightforward. There's only one really way that it could stop working. For other components, it could be more complex, right? There's different failure modes, different ways that the component could stop working. So think like a motor, you could have just a general stall, like you overload the motor and it stalls. It could overheat. It could become unbalanced and start vibrating. There's lots of different ways for something like that to fail, right? While you're doing this, just as a pointer, you want to give each failure an identifying number so that you can go back to it and refer to it. And I recommend starting the number with a letter that identifies which subsystem it's associated with. So say you have like a frame, right? And you're looking at different components in the frame and you want to talk about how each one could fail. Maybe start all the frame component failures with an F, right? So that you know that that's associated with the frame. If you have your electrical system, you could start all of the electrical failures with an E so that you know it's part of the electrical system. Something like that. You have some flexibilities, just as long as you as a team all agree on a standard and you document what those numbers mean. You can kind of do that however you want. But just be organized about how you're documenting these different failure modes so that you can refer back to them later on, because you'll be doing that. All right. So once you've got a big list of failure modes, then what you want to do is start to evaluate the consequences of each failure mode. So this is the effects part of FMEA. So what are the consequences for each failure mode? So you can think about this as the local effects, like what happens to the part itself that's failing, what happens to that when this failure mode happens. Then the next higher effects, so does this failure propagate downstream through your glass box diagram? Like if this component fails, what happens to the next component that it's connected to in your system diagram, right? Does it propagate up and cause another failure, or is that failure localized to the one? And then you keep following that through and say, what are the ultimate end effects of this failure? So could this propagate all the way through and can cause, pretty catastrophic failure for the end of your system? Or, maybe it'll take out another part in the system, but after that, the failure is contained and everything else is going to be okay, right? So that's kind of what we're talking about, is how does that failure propagate through the system? All right, then you can assign a severity classification for each type of failure. So generally in MilSpec 1629A, it gives you a number. So a class 1 failure is considered catastrophic, whereas a class 4 is considered minor, and then you've got a 2 and a 3 kind of between there. So just make sure you agree as a team for definitions of what's a catastrophic failure, what's a critical failure, what's a marginal failure, and what's a minor failure. So that you can assign those classifications. So, if you want to make sure you and your teammate are working with the same definition there, just so that those numbers are somewhat consistent in your analysis, right? And there's a good example of doing that in section 4.43 in the MilSpec 1629A document that you can check out. All right. So once we've got our failures sort of identified, we talk about the effects of those and identify the criticality, the severity of each of those failures. Then you can talk about how do you identify that this failure has occurred. So if somebody's operating your system, is this failure going to be obvious to them, right? So failures that we can't detect easily can lead to more severe problems. We saw this in the video with the slide valve that was eroded. There was no good way for the operators to know that that had happened and that the catalyst wasn't staying inside of their reactor vessel. So that led to a more severe failure because they didn't know that that slide valve was broken, right? So we want to figure out ways that our failures can be identified and things that we can watch out for to make sure that the system's operating normally, and then shut down if the system's starting to fail before we end up with a really catastrophic failure. All right, so that covers FMEA, so that should get you started. And in the next video, we'll be talking about FMECA, so the criticality analysis part of this, where we'll be estimating the probability of given failure modes actually occurring. So go ahead and get started on looking at your system, making your glass box diagram, and trying to identify those failure modes. And then once you have a good grasp on the FMEA, you'll be ready to move on and check out the FMECA. All right, and we'll talk to you then.